12.5, arc length and curvature. This will be our last section of the semester. You will move into chapter 13 with Dr. Tucker in the spring. And we're going to actually go back to something that we have encountered earlier this semester. You saw a variation of this in probably Calc 2, I think it is as well, and it's arc length. So the first thing I wanted to remind you of is a formula that you've seen, and this one was this semester, for arc length. This is in parametric form. So arc length in 2 dimensions for parametric form. We use the lowercase s, and this is the integral from a to b of the square root of x prime of t squared plus y prime of t squared dt. And we extend it into 3 dimensions, and it extends just exactly like you would expect. We just have the extra component of z prime of t squared dt, and that's actually otherwise known as the magnitude of r prime. So this is for a curve in space. They can get kind of messy. They can, and sometimes there's algebra to simplify things and clean them up, and sometimes there isn't. I'm not expecting you to go digging too deep to try and figure out how to use a table to do something. It's not going to be like that. So if there's anything, at least we can vouch for the test that is more extensive antiderivative methods of things from Calc 2 chapter, what is it, 5 or 6? Can't remember, whatever it is, 7, thank you. Yeah, all the different table stuffs. It's not going to go that far into it. Yeah. Okay. So there is a little bit of algebra simplification though, and this one's an example of such a thing that we should be able to do without getting too far into the mess of it. So we're going to compute the arc length. You can tell we have a space curve here. We have 3 components. And we need derivatives of all those 3 components. I'm going to just do the derivatives within the formula. If you want to write them separately to begin with, that's fine too. But we're looking at the integral. It says my t value is going from 1 to 3, so I've got from 1 to 3 of the square root, and I need the derivative of each of the components. So what's the derivative of 4 natural log t?
4 over t.
4 over t, so this is 4 over t squared. What's the derivative of t squared? 2t, which is now going to be squared itself. And then what's the derivative of 4t? 4. Okay, so this is the original setup for what we're doing. And we will simplify what's inside and then look for a way to simplify it further. So this would be 16 over t squared plus 4t squared and plus 16 dt. Okay, this can simplify. It doesn't need to use substitution. It doesn't need any fancy tables or anything like that. Any ideas as you're looking at it how we might be able to do that, Alex?
We can give it a common denominator.
Okay, we could give it a common denominator. That might help, and it might help for the next part too. I don't have it written that way in my notes, but let's go with that and see how it works. So your common denominator would be what?
T squared.
Yep. Okay, so we have 16, and I'll combine it with the common denominator at the same time, plus 4t to the 4th plus 16t squared over the t squared, right? So we could actually take the square root of the denominator. That part would be fine. How about the simplification of the numerator then?
Please square it?
So, kind of.
Well, you could just factor out 4.
Factor out the 4.
Okay, we can factor out the 4. Okay, so let's do that as well. In fact, let me do that over here to the side, so I'm hopefully going to not run out of space. So if I factor out the 4, I'm going to have a 4, and I'm going to have a t squared here. That will simplify to a 2 and a t out in front. What's left underneath the radical then is, and I'm going to put it in descending order, so I've got t to the 4th plus 4t squared, and then plus 4. Those were good steps. What do you notice underneath the radical, the second radical now?
both get out, or the whole thing can get out.
Okay.
Or second radical, sorry.
The second radical. The first piece definitely does. I'll actually write that down since you mentioned it. So this is a 2 over t at the first radical. What about the square root of t to the fourth plus 4t squared plus 4?
Split it 2 parts.
Okay, how does it factor?
T
Plus
squared
T.
plus
It could be two squares.
T plus T.
T squared, what's next?
plus 2.
Plus 2,
All that squared.
all of that squared. So it is completing the square, Adeline, but it's actually squared already. It's a perfect square trinomial.
That's nice.
Yeah, it is. It's very nice. And we don't have to have done it the way we did of factoring out the 4 and factoring out the t squared. It depends on where you notice it along the way. So up here at this point is actually where I have it in my notes. I put it in order, right, with the t squared component at first, the constant in the middle, and the one at the last, and I factored it from there. But it's kind of ugly factoring because it's got some, denominators in it and stuff like that too. So there's a couple different places along the way where if you happen to notice what it's doing, you can make that adjustment. So when I have this piece squared and then square rooted, those of course are going to cancel. And so I'm just going to get t squared plus 2. That's much nicer, right? So yes, it's a little bit messy, but it really doesn't involve any integration techniques. It involves a little bit of algebra. And then if we distribute the 2 over t back through, we would have 2t and then plus 4 over t dt. And what's the antiderivative?
T squared plus 4 natural log of absolute value of t.
Mm-hmm. And then we would evaluate this at 3 and 1, right? And if you wanted, because our t values are positive, you could leave the absolute values off of that, and it would be okay on this one. So if I put this in, I'm going to have 9 plus 4 natural log 3, and then minus 1 plus 4 natural log 1. It'll simplify a little bit. What can simplify?
Can you divide, do the...
It's easier than that.
It's just 8 plus 4 natural log 3 because the natural
Okay.
log 1 goes to 0.
Yeah, this one is actually equal to 0. But if it were a natural log of something else, then yes, you could combine them with a division of the pieces. That would be fine.
Okay.
But this one's actually 0. And then, Caleb, you mentioned I can combine the 1 and the 8, right? So I've got 8 plus 4 natural log 3. Another version of this, although I don't expect you to change it, but another version of this would be to say that this is 8 plus the natural log of 81. So where did the natural log of 81 come from?
Squared.
Or can be the exponent.
Properties of logs, so I can move the 4 as the coefficient up to the exponent of the 3, and 3 to the 4th is 81. So those are another version of it. Not necessary for you to do it, but if you looked into some other resource or wanting to confirm an answer, then I want you to realize it's the same thing. Is that good? Yeah.
And if Dr. Chin tells you to have natural log 3 memorized, you don't want us to convert it.
I do not want you to convert it. This is my exact answer. We will leave it just like that. All right. Definition. It's our last definition of the semester. Isn't that crazy? Last one. This is a definition of something called curvature. Okay, so let C be a smooth curve in the plane or space, either way. It's given by the position equation R of S. That should say R of T. I don't know why it says S. Let's be consistent. Let's just change it to a T. Everything else I have later is a T. R of T. Then the curvature K at T is, so it's the magnitude of the unit tangent vector divided by the magnitude of the derivative of the position vector. Or another version of that is that we actually have the magnitude of the cross product of the derivative and second derivative of the position vectors divided by the magnitude of the position vector's derivative cubed. Now, you might look at that and say, well, which one's easier? And the answer is they're actually both pretty messy. We're going to do one of each as an example. But you might still think, well, how do I know which one to use? And so just a general rule of thumb, the second one right here, it works well, or maybe it's more preferable when t is given. All right, so if you have a value for t given to you, this one is probably the one you're going to want to go with. And if you don't, you probably want to go with the other one. But neither one are actually very easy to compute. Okay? So you're going to want to write small on your next page, at least to some degree, so you don't run out of space because there are quite a few steps. So our first example, the directions are the same for both of them, says to find the curvature at the given point. And they actually give you a point on this one on number 2, whereas on number 3 here in a moment, we do not have a point given. So since I'm given a point, we're going to use the second version of the formula that was on the previous slide. Okay? So let me write it at the top, the two versions that we have, so that we'll have them as a reference on both slides. So we have the magnitude of t over, check to make sure I don't miss any pieces as I'm writing them. And then another one is, or another version of it, I'll just put equals in between. Magnitude of r prime, r double prime, or r prime cubed. I think I got all the pieces. Does that look right? Compare back and forth. Looks okay. All right. So we're going to use the second form here for example number 2. We're going to use this one. And so as you can see, that means I need the derivative in the second derivative. So that's what we're going to find first. So we're going to find our derivative. The second derivative is going to be actually pretty nice on it. So what's the derivative? And we'll just do it component-wise since it's already given to us that way. What do I get? I'll start you out 1. What's next?
2 cosine 2t.
Good.
3.
And 3. Good. Second derivative.
0 and then negative 4 sine 2t and 0.
Okay, so far so good?
Yes.
So it's kind of nice when things oscillate, which is the trig functions that we deal with most of the time, the sines and the cosines, and it's kind of nice when the powers of, go down with our polynomials, which these do. And then I need each of these evaluated at t equals 0. So at t equal to 0. So we're going to do r prime of 0. So if I put in 0 into the 1, 2 cosine 2t, and the 3, what is the vector that I get?
1, 2, 3.
It is. And if I put in 0 into the second derivative,
Straight zeros.
I get straight zeros.
That's nice.
Is it okay?
Yes.
All right.
So we don't have to find the theoretical repair.
Not for this one because we were given it at a particular point.
Okay.
Correct. The next one is going to be more messy because we don't get to put in 0 for t, right? Yeah. Did I hear you say you're excited about it being messy?
No, it was sarcastic.
It was sarcastic, okay. All right, so we need the magnitude. Well, we need a couple of things. We need the denominator, which is the magnitude of r prime of 0, and then cubed. And then we're going to also need the cross product. So it doesn't matter which one we do first. I've got the magnitude written first in my notes, so that's what I'm going to do first. So we're going to do the magnitude of r prime of 0. And so that's the square root of each of the components squared. So 1 squared plus 2 squared plus 3 squared, which is what?
5. No.
14.
It's 14. Okay, so that's going to be my denominator, and then it'll be cubed in the denominator in a minute. And then I need the cross product of these vectors that we found before. So it is. In general, it wouldn't be, so let me write it in, but you're right, for this one it will be all zeros. So I have a 1, 2, 3, and I have the zeros on the bottom row, and because of the 0 on the bottom row, when I do this in the 2 by 2 determinants, I'm going to get a 0 row, which everything's going to get multiplied by 0. So this is going to give me And remember, cross products give you a vector, not a scalar, so you get the vector 0, 0, 0. Okay? Now, in particular then, if you're wanting to know what is the magnitude of this 0 vector, you don't really have to compute it, right? That is, I'm sorry, it's cross. It is just going to be 0. And that's the numerator that I'm going to need in a moment for the curvature formula. So my curvature formula says that I'm going to have, let me write this in down here just so it's in this correct spot. I need the magnitude, and this is at 0, so all of mine are at t equal to 0 here for this particular one. So on the top, I have 0. On the bottom, I actually have the square root of 14 cubed. But of course, that's going to give you 0. The curvature is 0 here.
Wait, it's the curvature.
What do you suppose curvature of 0 would mean?
It's a straight line.
Not curved.
It's flat. It's not curved, right? It's straight in some fashion, right? Good. Okay. The next one's messier. It's messier because we're dealing with something where we don't have the t-value given. So let me actually take this onto the next slide. So we're going to want this piece of it. So we're going to have that curvature formula we're going to be working on. So don't have it written in here, but do you remember how we find t of t? That was our last lesson. What did you have to do?
You found
Take the derivative
of R.
and magnitude.
Okay, so we have to find a derivative of r, which is part of what the formula is anyway, so let's start there, okay? And we'll continue on with what we need to do next. But yeah, you guys are remembering, that's good. So r prime of t, this one's not given in component form. It's actually, this is a space, not a space curve, right? This is in 2 dimensions. That's fine. I did that on purpose because it's going to be messy enough with just your 2 dimensions. So we're going to give an example of that one. All right, so derivative of 4 cosine 2 pi t I plus 4 sine 2 pi t j.
Negative 8 pi sine 2 pi t I
Mm-hmm.
plus 8 pi cosine 2 pi j tj.
Okay, so pretty good with that. Good deal. And then what are we supposed to do to find t prime after we have r prime of t? Or not t prime, to find t of t after we find r prime of t.
It's that over its magnitude, right?
Yes. So the t of t is r prime of t over its magnitude, right? So what do we need to find next? The magnitude of that, right? Okay, so we need to find the magnitude of r prime of t. So magnitude is going to be finding the square root of each of the components squared. So we have negative 8 pi sine of 2 pi t squared plus 8 pi cosine of 2 pi t squared. Now what?
It's going to be 64 pi squared sine squared of 2 pi t.
Mm-hmm.
Plus the same thing but cosine,
Mm-hmm.
which just becomes 64 pi squared.
Yeah. Okay, so if we were to factor out the 64 pi squareds, right? If we were to factor those out, what we would be left with is sine squared plus cosine squared of the same angle. Yeah? And sine squared plus cosine squared is 1. So we have our square root of 64 pi squared. That's all that remains, which would be 8 pi. So our magnitude of r prime of t is 8 pi. So if I want to find, and I do, I want to find t of t, we will have this 8 pi as the denominator of each of the components of r prime of t. But that's actually pretty nice. Yeah, it actually works out really nice. So I just end up with a negative sign of 2 pi t I plus a cosine of 2 pi t j. Okay, we found, I think there was a typo actually in what I wrote before. I did, hang on. Up here, whoa, this is t prime. Is it written in your notes right over here? And I just copied it down wrong? It is. I did miss a piece. T prime, okay. Oop, there it is, okay. So in order to find curvature now, I need t prime, and I have this t, so I can find t prime next. I already have the denominator part because I already have r prime of t and the magnitude even, so I find all that already. So I need to find t prime of t. Okay, so like the same song, second verse, more trig, right? So what's the derivative of negative sine 2t pi, 2 pi t I?
Negative 2 pi cosine 2 pi t.
Negative 2 pi cosine 2 pi t I. Good. And then what's the next piece?
Negative 2 pi sine 2 pi t. It's like a tongue twister.
Yeah, it is. Pi t I j. All the letters in there, yeah. Okay, there's the derivative. And then we're going to find the magnitude of that. But again, it's going to feel a lot like the magnitude we already found, right? The square root. We have negative 2 pi cosine 2 pi t squared plus negative 2 pi sine 2 pi t squared. And what's going to happen besides me running out of space? Same thing we did before, right? So when I square each of these, I'm going to get the 2 pi's being squared. The negatives are going to go away. So I'm going to have 4 pi squared in both components. And then I'm going to have, which one was first, cosine? I'm going to have a cosine 2 pi, cosine squared 2 pi t, and plus the sine squared of 2 pi t. And of course that's 1, yeah? So this is going to equal 2 pi. And curvature is actually going to be very nice. The curvature should be the t prime magnitude that I just found, so that's 2 pi, over the magnitude of r prime, which I found up here, right? 8 pi. And that will end up giving me 1/4.
Will the k always be easy when we do it in this way, or
I
it's
can't
just
promise. This is a nice one that worked out nicely. But, I mean, think about what you're doing. I mean, you're taking derivatives of derivatives. So especially when you're dealing with trig functions, you're going to get a lot of repetition of values that are going to keep showing up. So that part should work out nicely. Yep,
Will
no?
the curvature normally have a t in it, and this one just didn't because it was trig stuff and they all canceled?
Will they normally have a t in it? Yes, they would normally have a t in it. This one is nice and trig canceled into Pythagorean identities, but wouldn't always have to do that, yeah.